Hey guys, I'm here with OpenQuant, ready to solve question number 3, 2D grid game. So this game is a hypothetical where we have our character trapped in a 6x6 grid, and he starts in the top left corner denoted 1, 1, and can only move right and down. Let's illustrate the problem. So we have our grid, which in this case is a square, and 1, 2, 3, 4, 5. 1, 2, 3, 4. This is our 6x6 grid. So right here is the 1x1, and here is the 6x6. 2, 2, 3, 6. And our character can only move right or down, and he can do these moves in any desired order, and the goal is to reach the end. The first subproblem asks us to compute the number of ways that our character can get from the top right of the grid starting location to the bottom right. So for reference, here is our grid that we drew up in the problem explanation. So we want to get from here to here and compute the various number of ways that we can do so. So I find that when approaching such a problem, it's helpful to just walk through some cases that are valid. So we have a very simple case where we go all the way to the right and then all the way down. That's one. Then another random case, we go down 2, over 2, all the way down, and then all the way to the right. And then a third and final case, let's say we go all the way down except 1, all the way to the right, and then down. So for each of these cases, let's number them 1, 2, 3. We can actually write out using characters what the path looks like. So for the first one, it was right 5 times. So right, 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 and then down 5 times. For the second one, we went down twice, right twice, then down 1, 2, 3, 1, 2, 3, and then right 3 times, 1, 2, 3. And for the third and final case, we go down 4 times, 2, 3, 4, right what looks like 5 times, 2, 3, 4, 5, and then down 1 last time. So here we have 3 cases, and they give us a lot of information. And now that we have a few examples to study, let's look for a pattern. So right off the top, I noticed that in all 3 cases, there are 10 total characters. And by character, I mean either right or down. And furthermore, I noticed that there are 5 R's and 5 D's. And the only difference between these 3 cases are the order in which they appear. In fact, we can generalize this using a combinatorics approach where we have our 10 possible moves, 10 characters, and amongst these 10, 5 of them are R and 5 of them are D. And we can choose them accordingly, where we have 10 total options and 5 of them are R. So this is the number of ways to choose our valid R's, and this is the number of ways to choose our valid D's. And it turns out that these 2 expressions, of course, are equal, and they both represent the same quantity, which is the number of ways to get from our point 1, to our end point 6. I'm going to now briefly just evaluate the expression 10 choose 5 to prove that you shouldn't shy away from such computation. And I also do feel that on a quant interview, it would give you a few bonus points if you were able to just quickly do such calculations. So this expression is 10 factorial over 5 factorial, times 5 factorial. And that's just by definition of the choose expression. And this further reduces down to, we can cancel out the last 5 terms of the 10 factorial with one of these 5 factorial expressions to get 10 times 9 times 8 times 7 times 6, and then the remaining 5 are all canceled out by one of these terms, and then just divided by a single 5 factorial, so 5 times 4 times 3 times 2 times 1. We can then begin to do a little cancellation, so this becomes a 2, this becomes 3, this becomes a 2, this becomes a 3, and we are left with 2 squared times 3 squared times 7 all over 1. This is 4 times 9 times 7, or 63 times 4, or 252. Alright guys, the second part of this question asks us to generalize the above process to an arbitrary n by m dimension grid. So let's draw what this arbitrary game would look like. So we have our 1 by 1 right here, and then we have this is the nth, second, third, fourth, this is the nth row, and then for m columns we have 2, 3, 4, and then m. And we want to get all the way down to here, which is the n by mth entry. This is where we win the game. So we can start by using a similar approach to the above problem, which is counting the number of ways that we can move right and the number of ways that we can move down. So because this game is one index, meaning that we start at the first row in the first column, there are m minus 1 valid moves to the right, so m minus 1 r's, and n minus 1 downwards movements, giving us a total of m minus 1 plus n minus 1 equals m plus n minus 2 total moves. And from this total number of moves, we want to select, again, like we were doing in the previous subproblem, the number of ways to move to the right or the number of ways to move down. So this would yield identical statements, m plus n minus 2, choose m minus 1, or m plus n minus 2, n minus 1. And this would be the theoretical number of ways to reach our endpoint for an arbitrary n by n dimension grid, n by m. And before we wrap this problem up, I would like to prove that these two expressions are indeed equivalent. So we can start by doing m plus n minus 2 factorial divided by m minus 1 factorial, and the second term in this denominator is this one minus that one factorial, and that's n minus 1 factorial. This is also equal to, using a similar approach, m plus n minus 2 factorial in the numerator, and then n minus 1 right here factorial, and this second term in the denominator is m plus n minus 2 minus n minus 1, or m minus 1. m minus 1 factorial. And as we can see, these two expressions are indeed equivalent, proving that this is the total number of valid ways to win an arbitrary m by n dimension grid.